Hello, and in part 6 of these OpAmp talks, we're going to be looking at the summing amplifier. The first method that we've come across which can add together the voltages at 2 points in a circuit. It's based on the inverting amplifier, and a simple summing amplifier circuit looks like this. Now, this is a linear circuit, so we could analyse it by superposition, just setting each of these two voltage inputs to 0 in turn, or we could just analyse it directly. And it's actually just as easy to do this one directly. We've seen the inverting amplifier before, and it has this form. The non-inverting input will just connect to a local reference voltage, in this case ground. The inverting input has a feedback resistor, which is acting to stabilize the output voltage, and has an input voltage coming through an input resistor here. I'll call this one R1 in this case, and RF there. The summing amplifier then just adds another resistor here, call it R2, and another voltage input, V2. But otherwise, it works in a very similar way to the inverting amplifier. Once again, we can assume that the action of the negative feedback is to keep the voltage difference between the two inputs effectively 0. So if the non-inverting input is at 0 volts, the inverting input must be at 0 volts as well. It's a virtual ground point. We can then apply Kirchhoff's current law to this node in the circuit here. The current flowing through R1 will just be given by V1 minus 0 divided by R1. That's the voltage difference across R1 divided by the value of R1. The current flowing through R2 will be given by V2 minus 0 over R2. Those are the two currents flowing into this node, so they must equal, when added together, the current flowing out of the node through RF. So that is the total current flowing out through RF. We can apply Ohm's law to RF. The voltage across RF, in the direction that this current is flowing, would be, well, it's 0 volts on this side, minus its V out in voltage on this side, minus V out, equals the current. This is the current here. That's just V1 over R1 plus V2 over R2 times the value of this resistor, RF. Voltage difference, current, resistance. It's just Ohm's law. And therefore, V out equals minus RF, the feedback resistor, times V1 over R1 plus V2 over R2. If these two resistors were the same, maybe they're both equal to R in, then we could write this as V out equals minus RF over R in, V1 plus V2. And that's why it's called a summing amplifier. The output is proportional to the sum of the two inputs. We can generalize this. There don't have to be just two inputs. We could have 3 inputs. We could have any number of inputs. And the total current flowing into this node here would be the sum of all of the input voltages divided by each of their input resistances. And it's that total input current which would be flowing through the resistance RF. So multiply that by RF, and that's the total voltage across RF. So that is equal to 0 minus V out. In other words, V out would just be equal to minus this, which is the general formula for a summing amplifier with any number of inputs. Let's have a look at an example. What would the output voltage be in this case? Well, we've got 3 inputs. We've got an input of 1 volt flowing through an input resistor of 10k. we've got an input of minus 2 volts flowing through a resistor of 20k, and we've got a third input of 1 volt flowing through a resistance of 30k. The feedback resistance is 60k, so Vout is just going to be equal to minus the feedback resistance times the sum of the V-ins divided by the R-ins. We're going to get that. Well, you might notice that this and this cancel each other out. So we're just left with minus 60k over 30k, in other words, minus 2. The output in this case would be minus 2 volts. You can play around with summing amplifiers in the simulator as well, and it would be a good idea to do that to get the feel of how they work. This summing amplifier has 2 inputs and a gain of minus 3. So the output would be minus 3 times the sum of both of these inputs. Currently both inputs are 0, but if one input went to 2, then the output will be minus 6. If both inputs went to 2, the output would be minus 12. If one input went to plus 2 and the other input went to minus 2, the output would be 0 again, because the sum of these two is 0. However, if I change one of these resistors to 20k, then this input here would now have twice the effect of this input here. I would have to set this to be plus 1 volt in order to get an output of 0, which I probably can't quite do, but I can get pretty close. We could see it this way. This output is now producing a range of values of 3 times its input. This one, however, is only producing at the output a range of up to 1.5 times its input. So if this one went to plus 2 and this one went to minus 2, you would expect the answer to be 3 times 2 plus 1.5 times minus 2, which would be 1.5 times 2, or 3. Fine. Before we leave summing amplifiers, I want to talk about a particular application of them. And that is this one. How to make a simple digital to analog converter. To take a binary number, which is represented by voltages on 3 inputs, and convert that to an analog voltage which has the value given by that binary number. And you can do that by having a summing amplifier which has different weightings on these inputs. X2 is the most significant digit in a 3-bit binary number. Supposing we had a binary number of 101, you would represent 1 by the voltage on X2, represent 0 by connecting X1 to ground, and represent 1 by putting a voltage on X0. And we've chosen these resistors so that X2 has twice the effect on the output as X1, and X1 has twice the effect on the output as X0. Just as in a binary number, this represents 4, this represents a number of 2's in the output, and this represents the number of 1's in the output. This is just 1 4 plus no 2's plus 1, or 5. If we choose the voltage that we put on these inputs when we want to represent a binary 1, then we can produce an output voltage here, which produces in volts the number represented by this 3-bit binary number. It works like this. Note, I've chosen a 2K input resistor and a 1K resistor here. So if I connect this input here to minus 8 volts, the effect on the output would be to increase it to 4 volts. Minus 8 volts here produces 4 volts here, because the gain of the summing amplifier from this input is 1 over 2, or a half. If I close this switch, then I'm changing the output by 2 volts. Because I'm connecting this point here to minus 8 volts. The gain of the summing amplifier from this input is minus 1 over 4, or a quarter. And minus a quarter times minus 8 is 2. So that produces a change in the output of 2 volts. Similarly, this one produces a change in the output of 1 volt. So if I set these 2 switches closed and left this switch open to represent the binary number 101, I would get 5 volts on my output. 7, 3, 2, 6, etc. It's a very simple way to make a digital to analog converter. It's not a particularly accurate way to make a DAC, because you do need very precise values of resistors here if this is going to be an exact representation of the state of these switches. But if you just want something quick and easy, and you're not worried about too much resolution, then this is a very simple way to make a DAC. That's it for this time. In the next of these talks, we're going to be looking at another type of amplifier which has 2 inputs. But this time, instead of adding up those 2 inputs, it subtracts them. And this is the differential amplifier.